You have lived with electricity your entire life. It powers every light in every room you have ever entered. It runs through the walls of every building you have been in. It is in your blood, literally, in the electrical impulses that fire between your neurons every time you think, feel, or move. Your heart beats because of electricity. Your brain runs on it. You are, in a very real sense, an electrical machine. And yet, if someone asked you to explain what electricity actually is, what would you say? Most people cannot answer that question, not clearly, not fully. We use electricity the way we use language, constantly, instinctively, without stopping to examine the thing itself. We know what it does. We know how to use it. We almost never ask what it is. The answer to that question took 2,000 years to find. It required experiments with kite strings and lightning. It required a self-educated blacksmith's son who taught himself physics by reading borrowed books in a candle-lit room. It required a Scottish mathematician who turned the experimental results of everyone before him into equations that predicted the behavior of light. And it required the slow, difficult, often wrong process of science, the process of guessing and testing and failing and revising that is the only way human beings have ever learned anything true about the world. By the end of this, you will understand electricity in a way that most people never do. Not just what it does, but what it is, where it came from, and who found it. The story of electricity begins not in the 18th century, not in a laboratory, but in ancient Greece. Around 600 BC, a philosopher named Thales of Miletus observed something strange. When amber, the fossilized resin of ancient trees, golden and translucent, was rubbed with a piece of fur, it attracted small objects, feathers, dust, hair. They seemed to leap toward it. Thales wrote about this. He noted it. He did not understand it. For the next 2,000 years, almost no one understood it either. The phenomenon was observed repeatedly, recorded, discussed in natural philosophy. Various names were proposed for it. The Greeks called it electron, their word for amber, which is where our word electricity eventually came from. Medieval scholars noted that glass, when rubbed, behaved similarly to amber. Some materials attracted, others seemed to repel. There was clearly a pattern. There was clearly a principle, but no one knew what it was. The fundamental problem was this: electricity, as it exists in nature, is invisible. You cannot see it directly. You can only see its effects: the spark, the attracted hair, the lightning bolt. And for most of human history, the effects were so varied, so unpredictable, so difficult to reproduce consistently, that building a coherent theory seemed nearly impossible. It was not until the 17th and early 18th centuries that serious experimental work began. An English physician named William Gilbert in 1600 published the first systematic study of what he called the electric force, distinguishing it clearly from magnetism for the first time, and establishing a method of testing which materials could be electrified by friction. He called the materials that responded to rubbing electrics. And then came the most famous electrical experiment in history. A man standing in a field, a key, a kite, a thunderstorm. Benjamin Franklin is one of the most remarkable figures in American history. He was a printer, a writer, a diplomat, a statesman, and one of the founding fathers of the United States. He was also, almost as an afterthought in the popular imagination, one of the most important scientists of the 18th century. Franklin had no formal scientific training. He was largely self-educated, having left school at 10 to work in his father's candle shop and then his brother's print shop. What he had, in place of formal education, was an insatiable curiosity and a talent for experiment, for finding the simplest, most direct way to test an idea. His interest in electricity began in 1746, when he attended a demonstration of electrical phenomena by a Scottish scientist named Archibald Spencer. Franklin was 40 years old. He was already successful in business. He had no particular reason to become absorbed in natural philosophy. But he was transfixed. He bought Spencer's equipment and began experimenting. Within a few years, he had made several genuinely important discoveries. He identified what he called positive and negative charge, the two states of electrical imbalance that create the force we experience as static electricity. He discovered the principle of conservation of charge, that when one object becomes positively charged, another becomes equally negatively charged. He invented the lightning rod. And then came the kite. The kite experiment, which Franklin reportedly conducted in June 1752 in a field near Philadelphia, was designed to answer a specific question. Was lightning a form of electricity? The prevailing scientific opinion was that it was not, or at least that the question was unanswerable. Franklin thought otherwise. He flew a kite in a thunderstorm with a metal key tied to the string and a Leyden jar, an early form of capacitor, attached to the key. When lightning struck near the kite, electrical charge traveled down the wet string to the key, and from the key to the jar. Franklin touched the key and felt the familiar electrical shock. Lightning was electricity. Electricity was lightning. The implications were profound. For most of human history, lightning had been something beyond human understanding, the weapon of gods, the punishment of the divine, an expression of forces entirely outside human control. Franklin had shown it was a natural phenomenon, subject to the same laws as everything else. More than that, he had shown it could be managed. The lightning rod, which directed electrical charge safely into the ground, was one of the most immediately practical inventions of the 18th century. But Franklin did not know what electricity was. He knew how it behaved. He could describe it, measure it, harness it. The deeper question, the question of its nature, would take another century to answer. In the decades after Franklin, electricity became one of the most active areas of scientific investigation in the world. An Italian physician named Luigi Galvani discovered in 1780 that electrical stimulation could cause a frog's legs to twitch, the first demonstration of the connection between electricity and living tissue. He called the phenomenon animal electricity and believed there was a specific biological form of electrical force distinct from the static electricity Franklin had studied.
He was partially right.
Electricity does play a fundamental role in biological processes, but the force itself was not biological. It was universal. Galvani's friend and rival, Alessandro Volta, disagreed with the biological interpretation. He argued that the electricity in Galvani's experiment came not from the frog's nerves, but from the contact between two different metals. To prove it, in 1800, he built something entirely new, a stack of alternating zinc and copper discs, separated by cloth soaked in salt water. When he connected a wire to the top and bottom of the stack, current flowed. Continuously, without rubbing, without friction, without any mechanical input at all. It was the first battery, the first device that could produce a continuous, controllable flow of electrical current. The unit of electrical potential, the volt, is named for him. Within a year of Volta's announcement, scientists across Europe were using his battery to do things that had been impossible before. They split water into hydrogen and oxygen using electricity, the first electrolysis. They discovered new elements. They began slowly to map the behavior of electrical current in a systematic way. And in Denmark, in 1820, a physics professor named Hans Christian Ørsted was giving a lecture when he noticed something extraordinary. When he placed a compass needle near a wire carrying electrical current, the needle moved. It did not point north. It pointed sideways, at right angles to the wire. Ørsted stood very still. Then he repeated the experiment. The needle moved again. He had discovered that electricity and magnetism, which everyone had assumed were completely separate phenomena, were connected. A moving electrical charge created a magnetic field. This observation, confirmed and expanded by the French physicist André-Marie Ampère in the same year, was the beginning of the end of treating electricity and magnetism as different things. Michael Faraday was born in 1791 in a village outside London, the son of a blacksmith who could barely afford to feed his family. He received almost no formal education. At 14, he was apprenticed to a bookbinder, and in the shop where he worked, he read everything he could find: philosophy, science, electricity. At 21, he attended a series of lectures by the eminent chemist Humphry Davy at the Royal Institution in London. He took careful notes. He bound them into a book and sent them to Davy with a letter asking for a job.
Davy's response
is one of the more famous replies in the history of science. He told a colleague, "I have made many discoveries in my life, but the greatest was Michael Faraday." He hired him. Faraday spent the next 40 years at the Royal Institution, and in those 40 years, he changed physics forever. In 1821, he demonstrated electromagnetic rotation, the principle that a current-carrying wire in a magnetic field will rotate. It was the first electric motor. In 1831, perhaps his greatest year, he discovered electromagnetic induction, the principle that a changing magnetic field produces an electrical current in a nearby conductor. This is the principle behind every electrical generator ever built, every power station that has ever produced electricity, from the first one Edison opened in 1882 to every solar farm and wind turbine and hydroelectric dam operating today, works because of what Faraday discovered in his laboratory in 1831. But Faraday's deepest contribution was not a device or a technique. It was a concept. He could not do the mathematics. His education had given him none. He thought visually instead, in pictures and diagrams. And what he pictured when he thought about the space around a magnet or an electrical charge was something entirely new. He called them lines of force. Today, we call them fields. The idea was this: the space around an electrical charge or a magnet is not empty. It is filled with invisible lines of influence that extend outward in every direction, growing weaker with distance, but never entirely disappearing. When another charge or magnet enters this space, it responds to the field, pushed or pulled by the invisible structure of lines around it. This was a radical departure from the physics of Newton, which assumed that forces acted directly between objects across empty space. Faraday's field was something that existed in space itself, independent of the objects that created it or responded to it. It was one of the most important ideas in the history of physics. And Faraday, who could not write a single equation to describe it, spent years being patronized by the mathematical physicists of his era, who struggled to take a concept seriously when it came without proof. The proof came from someone else. James Clerk Maxwell was born in Edinburgh in 1831, the same year Faraday discovered electromagnetic induction, and he was everything Faraday was not. Formally educated, mathematically brilliant, the son of a wealthy family with connections to the best scientific institutions in Britain. He encountered Faraday's work as a student and recognized immediately that Faraday's intuitive concept of lines of force was correct. More than correct, it was the most important idea in physics if someone could find a mathematical language to express it. Maxwell spent 15 years finding that language. In 1865, he published A Dynamical Theory of the Electromagnetic Field, a paper containing 4 equations, now known as Maxwell's equations, that described the behavior of electrical and magnetic fields with complete mathematical precision. The equations showed, among other things, that electrical and magnetic fields could propagate through space as waves. And when Maxwell calculated the speed of these waves from the constants in his equations, he got a number he recognized immediately. It was the speed of light. He wrote, "We can scarcely avoid the inference that light itself, including radiant heat and other radiations, if any, is an electromagnetic disturbance in the form of waves propagated through the electromagnetic field." Light was not a separate phenomenon. It was an electromagnetic wave. And electromagnetic waves were not just theoretical. They were real, physical, propagating disturbances in the invisible field Faraday had described. Heinrich Hertz confirmed this experimentally in 1887, the same work that would eventually inspire both Tesla and Marconi in their race to build the radio. The chain was complete. From Thales observing amber in 600 BC to Maxwell's equations of 1865, 2.5 millennia of observation and experiment converging on a single, unified theory of electricity, magnetism, and light. They were all the same thing. So, after all of that, after Franklin's kite and Faraday's motor and Maxwell's equations, what is electricity? The answer exists at 2 levels. At the practical level, electricity is the flow of electrons. Electrons are tiny particles that carry a negative electrical charge. In a metal wire, electrons can move relatively freely, passing from one atom to the next when a difference in electrical potential, a voltage, pushes them. This flow of electrons is what we call electrical current. It is what lights your bulb, runs your motor, and charges your phone. But at a deeper level, the level Maxwell was describing, electricity is something stranger and more beautiful. It is a field, an invisible structure that permeates all of space, created by any charged particle interacting with every other charged particle. When you bring 2 charged objects near each other, they do not reach across empty space and grab each other directly. The first object creates a field. The second object responds to that field. The interaction happens through the fabric of space itself. And light, visible light, radio waves, X-rays, gamma rays, the warmth of the sun on your skin, is a wave in that field. A disturbance that propagates outward from its source at 300,000 kilometers per second, carrying energy and information across any distance through any vacuum, forever, unless something absorbs it. The electricity in your wall and the light from a distant star are the same phenomenon, seen at different scales and frequencies. This is not a metaphor. This is what physics actually says, and it has been tested to extraordinary precision. The electromagnetic force, the force that governs electricity and magnetism and light, is the best tested theory in all of science. Its predictions match experimental measurements to more than 10 decimal places. The ancient Greek, who noticed that amber attracted feathers, was observing the electromagnetic force. So was Franklin in his field with his kite. So were you the last time you turned on a light. Michael Faraday, late in his life, gave a series of public lectures at the Royal Institution called The Chemical History of a Candle. They were intended for children. They were attended by adults of every kind. They were recorded and published and have never gone out of print. In those lectures, Faraday did something that was characteristic of his best work. He took an ordinary object, a candle, and showed that everything about it, from the chemistry of combustion to the physics of convection to the nature of the light it produced, was connected to the deepest principles of natural philosophy. He wanted people to see that the ordinary world was not separate from the world of science, that the force in a lightning bolt was the same force that held atoms together, that the spark from a rubbed piece of amber was the same phenomenon as the aurora borealis and the signal in a nerve. He was right, and he knew it, even without the equations to prove it. Faraday died in 1867 in the house at Hampton Court that the Crown had given him as an honor for his life's work. Maxwell's great paper had been published 2 years before. Faraday had read it. He reportedly said that he was glad to have lived long enough to see it. He had spent 50 years drawing diagrams of invisible lines in the air around magnets, describing something he could see clearly in his mind and prove only with experiment, never with mathematics. And a younger man with a formal education had taken those diagrams and turned them into the most powerful equations in physics. That is how science usually works, not as a single bolt of lightning from a single mind, but as a slow accumulation. One person observing, another measuring, another calculating, another connecting, until the thing that was always there, waiting in the ordinary world, finally becomes impossible to misunderstand. The force was always there, in the amber, in the lightning, in the invisible field between every charged particle in the universe. It took us 2,000 years to see it clearly. Now you do.